while they're getting started, it was really late last night when we got the order, when I sent the order to the students, and when I sent it out, immediately Tice and Nemo had texted me back and said, can we go first? So props to them for setting the standard, setting the bar, and wanting to go first. So thank you guys very much for doing that, and thanks to Noah and Jody, who were scheduled to go first, for saying, yeah, they can have it.
It was kind. When you're ready.
Mic check, 1, 2. I wanted to do that. Hello, thank you for coming out today. Excited to give you the first presentation of the day on additive manufacturing. We did our research at Materials and Manufacturing Research in our Mechanical Engineering Department at UND.
You guys can take the mic off if it's more comfortable.
Yeah, if you do, I can make it taller too. There you go.
This is our team. Dr. Gupta and Sharma and Gabe really helped us a lot with our presentation and everything. And I'm Tice Seewalker, and this is Nehemiah coming out great. And here's our outline for the presentation. Basically, we're going to start with the introduction, move on to the background of the problem, instruction, evaluation, stress testing, and non-destructive evaluation of understanding mechanical performance. RY for understanding additive manufacturing and 3D printing. I want to say I chose this topic because my older brother is really into 3D printing, and I went out to a STEM campus and I tried he was mentoring it, and it's kind of like a one-on-one, so it kind of opened up a lot more for me to be more intrigued in it.
I chose field because it's all about creating things in a completely new way, and plus there's technology that's rapidly changing industries from healthcare to aerospace. This slide illustrates the fundamental differences between additive manufacturing, which builds up objects, and subtractive manufacturing, which carves them out. Here are the key characters, why it matters.
This right here is the most common defects in additive manufacturing when 3D printing. So these are mainly caused by clogs, filament quality, improper bed level, layer separation. We do this so whenever you're trying to use it in a real life situation, it doesn't fail and when it most matters.
Image showcases the stereolithography, known as SLA, 3D printing technique where a laser and scanner precisely guides UV light to solidify liquid resin, creating objects with exceptional resolution and smooth finish. This method is commonly used for dental and jewelry models as well as high resolution prototypes. And here is our problem statement and what we're going to talk about. Understanding mechanical behavior and materials via extraction testing.
And here's one of the destructive testing we work with. It's called tensile destructive testing. See these we need to use samples, but we had samples of dog bones like that, and there's 2 different resins we use. As you can tell, we use it, we basically stretch it until the point where it stretches or either shatters off of it. So, yeah. And here's compressive testing. We use cubes and cylinders. As you can see, there's 2 different resins, as you can tell. Here's the durable, and here's the clear. This one's more like a plastically used sand. This one's more like glass. As you can tell, it actually shattered. And that one, then it just got squished into a pancake. And here we basically just explain that for test out tensile. You just pull it basically until something happens. That one slides away.
The graph illustrates stress displacement relationship for each resin during tensile testing. Durable V2 exhibits a plastic behavior, meaning it can undergo significant deformation before failure. The stress initially increases with displacement, then positions indicating yielding, and finally drops sharply at the point of failure. Durable V2 is more ductile. Clear viewpoint 1 shows the brittle behavior stress increases with displacement until it reaches a peak, and then material fractures with little to no plastic deformation, as you can see here. It's the point where it breaks.
And here it basically explains how compressive testing works for 3D printed samples. It determines material behavior under crushing loads performed using cylindrical or cubic samples. Tests are conducted using compression rigs. You guys all know what a compression rig is. It compresses things. Outputs includes compressor strength and modules. And here you can see the compression tested data. Right here you can see the clear V4.1. Right here, that's basically the stress amount before it stretches. Here, it didn't really stretch as much as that one. And well, actually, this one is way more brittle, so it had more stress until it went up to the breaking point. This one doesn't stress. I'll explain. It goes up to a certain point and it actually shatters by itself. As you can see with this one, it doesn't have a shatter point like that one. This one, you can actually just squeeze and compress forever and ever, basically making it to a flat surface. Like that, and you just shatter it. And that one you have to manually stop. And here's our problem statement. Now we're going to be going into our non-destructive mechanical behaviors.
This is UT, known as ultrasonic analysis system. UT uses sound waves to find defects and analyze materials without damaging. It helps keep an eye on the condition of equipment over time, checking for wear and tear or other issues that can lead to failure. Here are some of the samples that we tested that use the ultrasonic analysis system on. And as I said, remember what it does. Okay. And here are some of the samples. We manually put in defects because, we're just good like that. Good. And yeah,
And here's actually the ultrasonic analysis system, the results of it, what you actually see through the sound waves. Right here you can see we use 500 frequency, so that's like big ones that hardly miss the spot. So as you can see here, there's the voids, that's the defects that we manually put in there. As you can tell, and here's like the strong area. Red shows the signals, while blue indicates energy loss due to any attenuation, like to avoid the defects that we manually put in there. So we do this to basically see how the samples and different resins will work under failure, basically. So basically preparing it for real world situations. And here's the Keon's 3D profilometer. We use this for non-contact surface profiling. As a non-contact surface profiling too, it captures 3D surface topography with sub-micron accuracy. It measures height, roughness, and step dimensions. It's ideal for analyzing surface defects, layers, consistency, and 3D printers. And here, as you can actually see, I used a close-up of it, like samples, but if you actually have the dog one sample 3D printed, you will not be able to see all this right here. Like they actually got tiny pores in them, as you can see right here. And right here, you can kind of see a slight curvature going down. You cannot see that on the samples. So this is really helpful for pointing out the defects and stuff. And here's our conclusion. Additive manufacturing is not just a tool, but a catalyst for change, offering exciting possibilities for innovation, efficiency, and sustainability in manufacturing landscape.
Great.
I'm gonna put Craig in here because he's a very. I wanted to put Craig in here because he's a great spirit to be around, great soul, great person, always funny, always brings the vibes up in a room. He's like the LeBron James of the nature camp, we could say.
All right, so, does anybody have any questions for them? Sure.
When would you, why is this relevant to everybody here? Like, why would we need to pay attention to defects in what you guys tested and stuff?
So actually, 3D manufacturing is like, metals and stuff. It's like you use that every day for something. So this is basically trying to create new materials for real life problems like jewelry. You make it for dentures and everything, like your earrings and stuff like this. It's a new material that they're trying to introduce to the world for more purpose and more stuff to be used.
So it could be potentially stronger for like even building.
Yeah, and
buildings
it's
and
cost way less.
bridges and-
Yeah, it's cost free, and it's like you use it as tools and everything. Does anybody else have a question?
All right, well, let's go around the floor.